with topic 10, looking at the limit as x approaches c. And so yesterday we looked at methods of when I'm evaluating a limit at a specific x value, if I can plug in an x value, that's going to tell me my answer. Sometimes though, like on number 3, I'll need to simplify the function first by factoring, and then I can plug in my value. So far, we'll make a little diagram. We know that to evaluate the limit as x approaches c, I can plug in. So I always want to do this first. And if I get my answer, that's great, I'm done. But if it's indeterminate, so that's the form 0 over 0, and we had that example on number 3, the first time we plugged in -2, we got 0 over 0. So we had to factor it. So then I want to factor. But in our next example, we're going to see that, not our next one, on our second example today, we're going to see that instead of factoring, I want to simplify it by multiplying by the conjugate. So that will be our next way we can simplify. And then after we've simplified, either by factoring or multiplying by the conjugate, we'll go back to plugging in to get our answer. So we'll try to plug in first. If that doesn't work, we'll simplify by factoring or multiplying by the conjugate. And then after simplify, we'll go back to plugging in. And then, of course, to reinforce these concepts, we can look at these functions in our graphing calculators and use their graphs or their tables to help evaluate the limit. So, example, we had 3 yesterday. Actually, did we do 4?
Just
3. We did 3. So, number 4. I have the limit of 3 minus the square root of x over 9 minus x. And I want to evaluate this as x approaches 9. So I immediately see if I plug in 9, I'm going to get 0 over 0. So I need to simplify this one. And my methods of simplifying are multiplying by the conjugate or factoring. And remember, the conjugate is when you see a square root. Typically you want to use that method, and it would be the opposite sign. So the conjugate of the numerator is 3 plus the square root of x. But this one is actually kind of tricky. I actually can factor 9 minus x. So if you think about, what if this was 9 minus x squared? How would I factor that? It's the difference of 2 squares, so I would factor it into 3 minus x times 3 plus x. And I get that by taking the square root of 9 to get the 3 and then the square root of x squared gives me the x. So I can factor 9 minus x by using that difference of squares method. So I have two binomials, 1 plus, 1 minus. The square root of 9 is 3. And the square root of x I can write as the square root of x. And now I see this works because in top I have that factor 3 minus the square root of x. And now that factor that's in both the numerator and the denominator divides out. So I can rewrite this as 1 over 3 plus the square root of x. And now through direct substitution, I have 1 over 3 plus the square root of 9 gives me 3 plus 3, which is 6. So there's my answer. So that's a method by factoring. If I had not recognized that I could factor 9 minus x, and the reason why I did recognize it is because 9 is perfect and there's a minus sign. So I can factor it like the difference of two squares. But if I didn't recognize that, I could use the conjugate. So we'll go ahead and work that method out. So I have the limit of 3 minus the square root of x over 9 minus x as x approaches 9. And the conjugate would be multiplying top and bottom by 3 plus the square root of x. So again, the conjugate is the method you want to use with the expression that has the radical in it, and you just take that expression and use the opposite sign. Alright, so when I do this, 3, I'm going to FOIL the top, so 3 times 3 gives me 9. And then I have 3 times the positive square root of x plus negative 3 square root of x. So those middle terms cancel out, those outer and inner terms. So now just the last term, I have the negative square root of x times the positive square root of x. So that gives me just minus x. So the negative square root of x, the last term times positive square root of x. I know the square root of x times the square root of x is x, and then I still have that minus sign. So that's how I've got the minus x. And now I don't want to FOIL the bottom because now I have that common factor, so I'll just rewrite it. And now I can show that I can divide out this common factor on top and bottom. And then again, I'm left with 1 over 3 plus the square root of x. So if I plug in 9 again, I get 1/6. Alright, example number 5. I have the limit of 2 minus x over the square root of x minus the square root of 2 as x approaches 2. So this is another one that I can also factor because in top I have the minus sign and I can take the square root of both these numbers. And if I take the square root of 2, it's the square root of 2. If I take the square root of x, it's the square root of x. So if I first work this one by factoring, I'm going to rewrite it as the square root of 2 minus the square root of x times the square root of 2 plus the square root of x. And that's the difference of squares factoring method for 2 minus x. And then now on bottom, I have the square root of x minus the square root of 2 But I want to rewrite that because my square root of 2 is first, so I'm going to rewrite it as the negative square root of 2 plus the square root of x. I still cannot factor out because I still don't have anything in common, but I can take this bottom and factor out that negative sign. So I'm going to rewrite it one more time. The top is going to stay the same. And now on the bottom, I'm going to factor out my negative sign. And then I'm left with positive square root of 2 minus the square root of x. And now I have a common factor on top and bottom. So it divides out. So it has to be exactly the same to divide out. And sometimes we have to create it by using our algebra. And then now I have in top the square root of 2 plus x divided by, don't forget that negative 1 in the bottom. If I plug in my 2 now, that gives me the square root of 2 plus the square root of 2 divided by negative 1. And so I can write this as, I know anything divided by negative 1 is negative, and then the square root of 2 plus the square root of 2 would give me 2 square roots of 2, so I can write it as negative 2 square root of 2. And that would be my final answer. Alright, we'll do the same one by the conjugate now. Because some of you may see the factoring method better, and some of you may see the conjugate method better. Alright, so same problem. The limit of 2 minus x over the square root of x minus the square root of 2 as x approaches 2. And if I'm using the method of multiplying by the conjugate, I'm going to look for my expression that involves radicals, or one radical, and I have it in the denominator. So I'm going to just change that sign to a positive. Square root of x plus square root of 2, multiplying 2 top and bottom. Alright, so in the numerator, I don't want to multiply those together. I only want to FOIL them together when they are conjugates. So I'm just going to rewrite the top as 2 minus x times the square root of x plus the square root of 2. Alright, I know because these are conjugates that inner and outer terms cancel out, so I'm only going to multiply the first and last terms. So the square root of x times the square root of x is just x. And then the negative square root of 2 times the positive square root of 2 gives me minus 2. And I still don't have the same factor, but I see that I'm close. So I know I need to rewrite the bottom as negative 2 plus x. And then I'm going to rewrite the bottom by factoring out the negative sign. So now I have the negative in front and then 2 minus x. Now my common factor I can divide out. And I'm left with the square root of x plus the square root of 2 over negative 1. And then plugging in my 2 will give me negative 2 square root of 2 again. Alright, so we're done with topic 10, so if you have time, and today or tomorrow, go ahead and start that assignment while it's fresh on your mind, so you can remember those methods. And now we will move on to topic 11. Okay, so we are going to look at one-sided limits. And so first we're going to consider special cases. Alright, so consider the equation f of x equals 2 plus the square root of x. Alright, so from pre-cal, I know this is a square root function, constant added to it, so it's shifted up 2 units. So it's going to look, that's 1, 2, it's going to look like that. So notice if I was to approach 0, I can't approach it from both sides. So this is a one-sided limit, and I can write the limit of f of x as x approaches 0 from the right, and to denote it's coming from only the right, I use a little plus sign at the top. And then so now if I only evaluate it from moving closer to 0 from the right, I know it equals 2. So the plus sign denotes from the right. Alright, so that's a special case, and that's because the graph of it, the domain, starts at 0, so there's nothing to the left of it. So next we're going to look at a piecewise function. Alright, so example 1. Use a graph to evaluate. So we're going to have to make a graph of our function, and our function is f of x equals, my first expression is x plus 1 for x is greater than 0. And then my second expression is negative x minus 1 for x is less than or equal to 0. Alright, so remember piecewise functions have 2 or more expressions defined on certain intervals. So I want to sketch a graph. I'm going to do just a little graph of it. I have the linear piece x plus 1, and it's going only to the right of 0. And if I plug 0 in, 0 plus 1 is 0, so I have that point starting at 0, 1, but it's open because the domain, the interval for this expression is just greater than 0. So I'm going to plot that point, and then this linear function has a slope of 1, so it's just going to go up. Okay. Now for my next one, it includes 0. So at 0, 0 minus 1 is negative 1. So I have the point 0, negative 1. Since it's included, it's closed. And then this graph, this expression is graphed for when x is less than or equal to 0, so it's moving to the left. So here's my starting point at negative 1. And this one has a slope of negative x. So I know it would come through there like that, but I'm only graphing to the left. So it's going to look like that. Alright, so from this graph, first evaluate the limit of f of x as x approaches 0 from the right. So I'm coming from the right, so notice this one would equal positive 1. And now I'm going to evaluate the limit of f of x as x approaches 0 from the left. And so now from the left, it equals negative 1. And then finally, what is the limit of f of x as x approaches just 0? And now that I've evaluated both the right and left side limits at 0, I can look and I can see, well, those don't have the same values. Because remember, the limit only exists if it's approaching the same thing from the left and the right. So I now know this limit of f of x as x approaches 0 does not exist. So remember, for one-sided limits, they may exist from the right or from the left, but that doesn't mean the limit at that certain x value does exist. Alright, so one more example of a piecewise function. Example 2. I have f of x equals, and this time we have 3 expressions for our piecewise function. So I have x squared for x is greater than 2, negative 7 for x equals 2, and 6 minus x for x is less than 2. And instead of graphing it, I'm going to use direct substitution. So, A, the limit of f of x as x approaches 2 from the right. So in order to evaluate this using direct substitution, I have to figure out which expression is going to the right of 2. So for the bottom one, I'll just start at the bottom. 6 minus x is graph for when x is less than 2. Since it's less than 2, that one's coming from the left. This one is equal to 2, and then my top one, the x squared function, is going to be graphed for when x is greater than 2, so that one is from the right. So now I know I'm going to plug in to the top function. So it's going to give me 2 squared, which is 4. And then now for b, we'll evaluate the limit of f of x as x approaches 2 from the left. And I know the expression coming from the left is the last one, 6 minus x. So I'm going to plug in my number 2 to that expression. And 6 minus 2 also gives me 4. And so now for c, the limit of f of x as x approaches 2, I know will equal 4, since that's what both my left and right side equal. Okay, so now we'll look at, so we've had part A, special cases, part B, piecewise functions, part C, evaluating vertical asymptotes. So example 3. I want to evaluate the limit of x squared minus 3x over x minus 1 as x approaches 1 from the left. Alright, just by looking at this equation, I know that 1 is a vertical asymptote because that's my 0 of my denominator. So when I'm evaluating it from one side, I'm trying to decide on that side, is it going to positive infinity or is it going to negative infinity? And if we use our sign analysis, that's going to tell us. So remember, on our sign analysis, we put our vertical asymptotes and our zeros. So if I factor the top, I have x times x minus 3 over x minus 1. And so the zeros will be 0 and positive 3. And then my VA is positive 1. So on my sign analysis, I want to put those values 0, 1, and 3. And then I'm going to test values in between 0 and 1, or values in between 1 and 3, to see if it's positive or negative. For this example, since I'm only concerned about the left, I'm just going to plug in between 0 and 1, which would give us a fraction, but that's okay. And let's plug in 1/2, because that would be between 0 and 1. So I have 1/2 times 1/2 minus 3 over 1/2 minus 1. Okay, and I'm not even going to work it out. So my top 1/2 minus 3 is going to be negative. Negative times a positive 1/2 is still going to be negative. And in the bottom, 1/2 minus 1 is going to be negative, and I know a negative divided by a negative is a positive. So now I know between 0 and 1, all my values are positive. So as I approach 1 from the left, if my curve is going up, that tells me that this limit is equal to positive infinity. And I'm going to go ahead and finish this sign analysis so we can see it. In between 1 and 3, I'm going to have, let's pick 2. So I'd have 2 times a negative number divided by a positive number, so it's going to be negative. So real quick sketch. Here's 1. That's my vertical asymptote. It's bigger on top, so there's no HA, but it's bigger by 1, so I know it's got a slant asymptote. And then I've got a 0 at 0 and 1 at 3. And then if we did the work, to the right of 3 is positive, to the left of 0 is negative. So if I go put those sign analysis below and above the x-axis, so to the left of 0 is below the x-axis, to the right of 0 and up to our VA is above it, and then to the left of 3 is below the x-axis, and to the right of 3 is above the x-axis. And this would have a slant asymptote in there like that. So now, here's 1. So as I approach 1 from the left, it's going up, so it equals infinity. If my question asked from the right, it's going down, and I would see to the right of 1, I have negative values, so that would tell me it equals negative infinity. Alright, example number 4. another vertical asymptote problem. What is the limit of 2x minus 3 over 2x squared plus x minus 6 as x approaches negative 2 from the right? So I definitely want to simplify this one first. So I'm going to rewrite it by factoring the denominator. So I have 2x minus 3 on top. And then 2x squared plus x minus 6. I have 2x squared, so I know that factors into 2x and x. And now the factors of negative 6, but I've got to make positive 1, and one of those factors will be multiplied by 2. So that's going to give me a negative 3 and a positive 2. Because right here I have negative 4x. Did I do that right? Negative 3 and negative 3 times 2 is negative 6. And now positive 4x minus 3x gives me positive 1. Okay, so 2x minus 3 cancels out. So I'm left with 1 over x plus 2. Now I see negative 2 is a vertical asymptote. So when I go to evaluate this, I want to do my sign analysis to see is it going to positive infinity or negative infinity. And I'm going to put negative 2 on my sign chart. Plug in something from the left. Plug it in something from the right. I'm going to choose the right first. Let's just pick 1. 1 divided by 3 would be positive. And now a negative value, so 1 divided by, let's say negative 4 plus 2 is still negative, so it is negative. So if I'm approaching negative 2 from the right, because of that positive sign, I know my answer is positive infinity. You could also use knowledge of what that graph looks like. We know 1 over x is in quadrants 1. This is how that the pre-cal skills also of knowing your functions help. We know 1 over x looks like this, with the vertical asymptote right there at 0. So remember, this is that function just shifted to the left 2 units. So my vertical asymptote, instead of at 0, it's going to be right here, and it look like this. So approaching negative 2 from the right goes up. Alright, last example of our vertical asymptotes. Maybe not the last example. Okay, number 5. The limit of x plus 2 over x squared minus 4 as x approaches negative 2. Alright, so I want to factor it first because I see the difference of squares in the denominator. So I can rewrite it as x plus 2 over x plus 2 times x minus 2. And now I see that my factor where x is equal to negative 2 cancels out. So I'm looking at as x approaches negative 2, and I forgot to write, no, it's right, just from negative 2, not one-sided limit. So now I see that since this factor cancels out, x equals negative 2 is a whole. can I plug in -2? Yes. And so if I plug in -2, that would give me 1 over -2 minus 2 is -4. And so since direct substitution worked, that's my answer. So remember, holes, the limit of that value of x not being one-sided or left, they do exist. And I don't have a sketch of this graph. I have a vertical asymptote at 2. So at -2, I have this point -2, 1, 4. So this graph on this side is going to look something like this. And so I can see as I approach -2 from both the left and right, they do both approach -1, 4. So when it's a hole, after you simplify it, direct substitution does work. Alright, example number 6. The limit of cotangent of x as x approaches pi from the left. Now, I'm going to say this is a non-calculator question. And if I'm wanting to evaluate this, first thing I'm going to do is plug in pi. What is cotangent of pi? So if I'm at pi right here, that point is -1, 0. I know cotangent is the ratio, not sine is y over x, so cotangent is x over y. So x divided by y is undefined. So direct substitution does not work. And I don't know how to simplify cotangent of x, other than writing it as cosine or sine, and then that would still give me -1 over 0. So I'm going to graph the function, cotangent of x. And if pi is undefined, that means it's a vertical asymptote on this function. Remember what the tangent function looks like? Well, the cotangent function looks similar. So what is cotangent of pi over 2? So right here at pi over 2, I have the point 0, 1. So the x value divided by the y value is 0. So I have a 0 at pi over 2. And the cotangent function at 0. So I'm just writing down my points. 1, 0. So again, 1 divided by 0 is undefined. So that is also a vertical asymptote. And very similar to the tangent function, it's going to go through like this. And then I know I would have a 0 at 3 pi over 2, and then another asymptote at 2 pi. So now I have a nice sketch of my function. And so now I want to approach pi from the left. So here's pi, here's from the left, and so now I can see it's going down. So my answer is -infinity. All right, and we will stop there for today.